Next up in our series of videos about solving word problems involving systems of equations is uniform motion applications. So we're going to use similar strategies here that we did in the previous problems, but we might draw some pictures just to help us along a little bit. So in this problem, Joni left St. Louis on the interstate, driving west towards Denver at a speed of 65 miles per hour. Half an hour later, Kelly left St. Louis on the same route as Joni, driving 78 miles per hour. How long will it take Kelly to catch up to Joni? So let's see, we have Joni. Pardon my crazy computer. Close your eyes if this makes you nauseous. Almost there. Okay, sorry about that, you guys. Get my cursor here and maybe it will not do that next time. Okay, so we have Joni. She left St. Louis. Driving towards Denver at 65 miles per hour. Then we have Kelly, who also left St. Louis, but she left a half hour later. And she's driving towards Denver at 78 miles per hour. When will Kelly catch up to Joni? So we know that rate times time equals distance. We have rate. We're looking for time. It's saying how long will it take? So what's our distance then? Well, we don't know that either. So why don't we write out some equations for now, just with what we know. So we know the rate is 65 times time, we don't know what that is, equals some distance. We know Kelly left a half hour later. We know her rate is 78 miles per hour. Her time is the same as Joni's, but minus a half hour. We're going to stick with hours just because we're talking about miles per hour, so we don't want to mix up minutes and hours. So we're going to say 1/2 for a 1/2 hour. Now we have these two equations. They're both solved for D, so we can use substitution to solve this. 65t equals 78 times t minus 1/2. 65t equals 78t minus 39. Subtract 78t from both sides, and we get negative 13t equals negative 39. Divide both sides by negative 13, and we get t equal 3. What does that mean? How long will it take Kelly to catch up to Joni? Well, Joni, her time is t, so Joni will have driven 3 hours. How long did Kelly drive? She drove a half hour less, so Kelly drove 2.5 hours before catching up. So there's one example of a rate times time equals distance problem. Let's look at another. So we have rate times time equals distance. I'm just going to keep that up here so we keep that in mind when we're writing our equations. A river cruise ship sailed 60 miles downstream for 4 hours and then took 5 hours sailing upstream to return to the dock. Find the speed of the ship in still water and the speed of the river current. So let's say the speed of the ship is x. And the speed of the river currents is y. So the river cruise ship sailed 60 miles in 4 hours. And it sailed back in 5 hours. So we're trying to find the rate. So when the river current is helping it along, it only took 4 hours. So the time times the ship and the current working together give us 60 miles. Now going the opposite direction when they were going against the current, it took 5 hours. This time, not only was the current not helping the ship, but the current was actually slowing it down. So we're going to subtract this time, and it still equals 60. Let's distribute both of these equations and see if we can figure out the best way to solve them. Well, maybe distributing isn't necessarily the best option. Maybe we can divide both sides of the equation by what we're multiplying by. So let's do that. So we're going to divide both sides of this top equation by 4 instead of multiplying it out, just so that we can keep these x and y's without having any numbers in front of them. So we'll have x plus y equals, 4 goes into that, 15 times. And then we will have x minus y equals 12. 5 goes into 60 12 times. And now we have a positive y, we have a negative y. We can use elimination to solve this one. So we'll just add these together. 2x equals 27. X equals 13.5. So we can plug 13.5 into any one of these equations for x. I'm going to plug it in here. So we'll have 13.5 plus y equals 15. Subtract 13.5 from both sides and we get y equals 1.5. So we can double check. Let's do that. So in our first equation we have 4 times x plus y, 4 times 13.5 plus 1.5 equals 60. 4 times 15 equals 60, and it does. Let's try the other one. 5 times 13.5 minus 1.5 equals 60. 5 times 12 equals 60, and yes, it does. So our current is 1.5 miles per hour. And our ship is 13.5 miles per hour. All right, last example before we take our next break. A private jet can fly 1,095 miles in 3 hours with a tailwind, but only 987 miles in 3 hours into a headwind. Find the speed of the jet in still air and the speed of the wind. So this is going to be very similar to the one we just did. Rate times time equals distance. So it can fly 1,095 miles in 3 hours. Tailwind but only 987 miles in 3 hours with a headwind. So let's say X is our jet and Y is our wind. So when the wind is helping us, we have our time, which is 3 hours, X plus Y equals 1,095 miles. In 3 hours, when the wind is working against us, we have to subtract the wind, and we get 987. This time, because we're distributing the same number, I'm just going to go ahead and distribute because it'll cancel out pretty easily. So we get 3x plus 3y equals 1095. 3x minus 3y equals 987. We'll add these together and we get 6x equals, not going to do that in my head, 1095 plus 987 equals 2082. We'll divide that by 6 and we get 347 miles per hour for the jets. Let's see if we can figure it out for the tailwind. So I'll plug 347 into our first equation. Distribute that. 1041 subtract 1041 from both sides. We get 54 equals 3y. Y equals 18. For the wind. Don't have a lot of space to double check these equations, but we'll give it a try anyway. So we have 3 times 347 plus 18 equals 1095. 347 plus 18 equals times 3, 1095. So that is correct. That does work. Let's try the other equation. We have 3 times 347 minus 18 equals 987. 347 minus 18 times 3 equals 987. That one works as well. We are good to go. So you guys can go ahead, work on problem 26, and I will see you at the next set of word problem types.